University. This is Office Hours at Duke University. Today, Dr. Miguel Nicolelis takes your questions about connecting brains and machines. Nicolelis is the Ann W. Dean Professor of Neuroscience and co-director of the Duke Center for Neuroengineering. His new book is Beyond Boundaries, the New Neuroscience of Connecting Brains with Machines, and How It Will Change Our Lives. In 2008, Nicolelis and his colleagues were able to use brain activity of a monkey in North Carolina to move the legs of a robot in Japan. To ask Nicolelis a question, send an email to live@duke.edu, tweet with the tag Duke Live, or post to the Duke University Facebook page. You can watch today's discussion again anytime on Duke On Demand.
Welcome to Office Hours. I'm Ashley Yeager, a science writer in Duke's Office of News and Communications, and joining us today is neuroscientist Miguel Nicolelis. Welcome to the program.
Thank you, Ashley.
You have a new book out called Beyond Boundaries, and in it you counter this idea that the brain has, specific parts of the brain have specific functions. How does your research counter that idea?
Well, for the last 20 years, we have been studying how distributed populations of brain cells interact to generate behaviors. And as you said, there was the dogma of the last century in neuroscience was that every function was allocated to a particular part, particularly of the cortex, this superficial part of the brain. And our research tested this idea by implanting sensors to read electrical signals from different areas of the brain to look for how these areas produce a particular function, motor control. And motor control of the upper limbs or the legs or the whole body. And we started looking for signals, and we found that we could recover information from multiple areas all over the frontal and parietal lobes, suggesting that that idea that it started 200 years ago, with the phrenology movement, in which you could, people, Franz Gall, this physician in Europe, used to say that he could define your personality just by measuring the bumps of your head. Because, if you had a particular trait in your personality, that part of your brain would grow, higher and produce a bump that he could identify. Well, this has migrated to neuroscience, and these experiments helped, I think, debunk that notion.
So you're saying the signals come from throughout different parts of the brain
Yes.
instead of certain areas?
Yeah, there are contributions that can come from all over. It's like an election. It's like a vote. Not every neuron has the same weight in the election, but you can recover information from multiple locations. And we are now finding that this is true for tactile processing and for all sorts of other things, gustatory processing, visual processing. And there are experiments by my colleagues here in the United States that show that if you blindfold a person, for instance, one of us, if we put a blindfold for just a few minutes, we will recover very strong tactile responses of us touching objects in our visual cortex. Oh, way back here, where people thought that only vision was processed.
And so also in your book, you talk about these brain signals as a neuronal symphony. Why a symphony, and what does that symphony sound like?
Well, that's a metaphor that I like to use. It is a symphony because you have players. Neurons are players in this symphony, and these signals are electrical signals that we record. We use hair-like filaments, hundreds of them, implanted in the brain to record this electrical music. And actually, we listen to it. To know where you are or to identify certain types of neuronal responses, we send these electrical signals to an amplifier, and then this amplifier sends the signal to a loudspeaker. And then we listen how neurons fire. And that's the analogy with music. So if you put hundreds of cells firing together, you create some sort of neuronal music. It's not the kind of music that we listen to, but we neurophysiologists are trained to listen to that. So since early in my work, I always made this comparison because it's very interesting. But it's a symphony, an orchestra playing without a conductor. There is not a single conductor. So it's a very democratic symphonic orchestra. There's no maestro, prima donna in front of the podium telling you what to do. It's a coherent composition, a collective composition.
And so with these filaments that you mentioned, is that getting at this idea of the brain-machine interface? Is that where this began?
Yes, this effort, this paradigm that we call brain-machine interface about 12 years ago, it started with an attempt of reading large-scale brain activity, large-scale electrical signals generated in the brain to try to understand the coding mechanisms that the brain utilizes to encode information and generate behavior. So that was our goal. We had, I'm talking about John Chapin and I. John Chapin was my mentor, a postdoctoral mentor at Hahnemann University in Philadelphia. Now he's at SUNY Stony Brook in New York. We both had worked together to try to understand how tactile information is encoded by the brain. And we found out, contrary to what the literature was telling us for 50 years, that it takes a population. It takes a large village, neuronal village, to encode tactile information rather than specialized cells. But people didn't think that that was convincing enough because our rats could not tell us what they feel when we did these experiments. So we decided to create a paradigm in which we could actually visually measure the output of a behavior, and motor behavior you can measure very precisely, and prove that populations are necessary to generate this behavior rather than individual neurons.
So we have a question here from one of our viewers. It's asking, is the brain's operation a lot more complicated than we thought?
Oh, yeah, much more complicated, yeah. There's nothing that compares to the brain but the universe. I always say that. There are as many cells in our brains as there are galaxies in the universe. So we're talking about something rather complicated. As my neurosurgeon teacher used to say in medical school, this is not orthopedic surgery. It is the brain, so be careful what you're doing in there.
And so, in terms of brain-machine interfaces, how can you use those to treat diseases like Parkinson's?
Well, the brain-machine interface concept is basically the ability to read in real time large-scale brain activity, so electrical signals. We are getting close now to collect signals from 1,000 neurons. We want to go beyond, but that's what the state-of-the-art is today. And in reading these signals right now from motor structures in the brain, extract from these signals motor commands, the voluntary motor intention of the subject to enact those movements into artificial devices. So the first major application that we thought over 10 years ago when I started is for restoring movements in severely paralyzed patients. So a patient that has, let's say, a lesion up here in the spinal cord that renders the patient paralyzed from the neck down, quadriplegic patient. Is very little that can be done today to restore movements besides physical therapy and rehabilitation. So our idea was to record the signals that are being produced by the brain of these patients because they continue to be produced for life. The patients dream about moving, they imagine movements. So you can record these signals with our technique from structures in the frontal and parietal lobe, decode these motor intentions, transform them in digital commands, and our plan now is to send this to a whole robotic vest, a whole body robotic vest that would basically enact this desire to move and carry the body of the patient. So the first application that we dream of and that we are about to implement in the next few years is to restore mobility in paralyzed patients. It turns out that by developing this technology, we found other applications. One of them, as you mentioned, in Parkinson's disease. It's a different type of brain-machine interface. In that interface, we are sending signals to the brain to try to correct a pathological activity that generates Parkinson's.
I think we have a video of a recent experiment you did. Let's take a look at that, and maybe you can talk to what we're seeing in the video.
Absolutely. Yeah, this is a mouse that was depleted of a key chemical called dopamine. And this dopaminergic depletion produces Parkinson-like syndrome. And you saw that the animal was paralyzed in the corner of that cage. And it happens that when we start stimulating the surface of the spinal cord of this animal, right in the back here, with a 300 hertz pulse, you can see that the animal now starts moving instantaneously. And he can now go to the other side of the cage and drink water. He's looking for sweet water there. And so the deficits that we saw, this difficulty to move and the tremor of the animal, are gone because we are able to disrupt the pathological electrical storms that were produced in the brain when the animal was Parkinsonian.
So could you translate that eventually to humans?
Yes, we already started to translate these studies in primates, and our preliminary results reproduce exactly what you saw. So that's the next final step, or the final step before you get to clinical studies. So we are finalizing that study, and if we reproduce this the way we reproduce in the first couple animals, we will be able to start testing this in subjects, in human subjects, probably next year.
So we also have a question here from Jackie. She's talking about a neurological damage that she's had, bleeding in her spinal column in the lumbar region. And so she had this damage about 1.5 years ago. And she's been able to regain movement in certain muscles, but certain muscles like her hamstring and her hip flexor aren't responding. She's wondering, could a machine be made to connect with the brain neurons that control those muscles and regain movement for her?
There are many potential applications of these brain-machine interfaces. In fact, I just came back from a meeting in Europe where people were discussing our alternative is to get the signals from the cortex, the higher motor centers in the brain, and project to a vest. Nothing impedes us or others to develop just a leg, a robotic leg, or a robotic arm vest. In fact, there are people doing that right now. For instance, for amputees that have lost arms or legs, people developing robotic limbs that would be able to respond to brain control signals that we record. In this case, sure, you could have localized actuators that help the patient that cannot move a particular limb or a group of muscles to restore their mobility. That is not what we're doing, but there are people thinking about that.
And so in terms of brain damage, if a part of the brain is damaged, then because specific locations don't control function, can that function move from a certain part to another part of the brain?
It's not necessary that the function moves. What happens is the brain reorganizes itself. I like to use the metaphor that's simple to understand. Suppose you are an airline controller and Chicago airport goes off because of big snow, right? And you still have to route the flights to California coming from New York. Well, what happens is that the flow of flights that used to go to Chicago seamlessly are transferred to some other cities in the Midwest or to other airports. That's basically what the brain does. Dynamically, if there is a lesion, if the lesion is too small, you don't even notice. There's not even a clinical symptom or a clinical sign because the brain takes care of that very easily. There is a plastic reorganization, a dynamic reallocation of resources for the brain to operate. As the lesion becomes bigger and bigger, of course, you start having symptoms and deficits because you surpass the limit of what the brain can do. But it's still, even at that level, the brain is reallocating resources to try to cope with the loss of tissue or the destruction of pathways in the brain.
Could this be what's happening right now with Congresswoman Gabrielle Giffords as she's recovering
absolutely, from... Absolutely. I'm sure that that's what is happening. And what is happening in neurology, I think more and more, is to try to take advantage of this phenomenon of adult plasticity that until 28 years ago, we didn't know existed. We thought that after a critical period in our development, that's it. The brain was consolidated and nothing could change. But now we know that throughout our lives, the brain can adapt to injury, and we can learn throughout our lives. So these are very much related, this phenomenon of recovery from injury and learning new behaviors and tricks. They are related by this mechanism of brain plasticity.
So I want to go back to something that you mentioned about this bionic suit that you're creating. To get to that point, you've done some research to have a monkey control either a pair of legs or a joystick and a robotic arm, but not necessarily moving themselves. Can you talk a little bit about those experiments?
Oh, yes. Yeah, we have progressed, of course, sequentially from upper limb control, which we demonstrated, lower limb control, locomotion of a robotic device under the control of brain activity generated by a monkey. And recently we also showed that we can extract from higher brain structures signals that could control balance, so the body balance. So now we are putting all together to test an exoskeleton for monkeys. So it's a robotic suit that will allow the entire body movement to be controlled by the voluntary activity of the animal's brain. So that's the first time that this will ever be tested. And this is perhaps one of the last animal tests that we'll do before we actually move to the clinic arena to try in about 3.5 years to make a human being recover full body locomotion with a brain-machine interface.
And so I want to talk a little bit about the experiment that you did where you had a monkey walking on a treadmill and it was sending brain signals over the internet to a robot in Japan.
Yes.
I think we actually have a video of that, and we're going to take a look at that. And there's a clip that kind of illustrates what's going on and talks about that story. So maybe we can take a look at that.
Brain activity of a monkey has been used to control the real-time walking patterns of a robot halfway around the world. Duke University researchers completed a demonstration that harnesses the brain cell activity associated with leg movement in a monkey, simulated here by computer animation, to manipulate the complex walking and standing tasks of a robot. The Duke team is working with the Computational Brain Project of the Japan Science and Technology Agency in Kyoto, Japan, to complete this research.
Not only could the monkey control both his legs and the legs of the robot at the same time, but when we stopped the treadmill moving here at Duke and the monkey stopped walking, using the visual feedback she was getting from Japan, she was still able to sustain the locomotion of that robot for a few minutes just by thinking.
And so in this experiment, you used a monkey. Was this Aurora?
No, this was Idoia.
Okay.
A cousin.
A cousin, okay. And so in your book, you talk about Aurora, and you talk about you talked about them as colleagues.
Oh, absolutely.
Can you describe a little bit about working with them, their personalities?
Oh, each one of them has a clear personality, and since you interact with them every day, and I used to interact with Aurora every day, really, literally, every day. In fact, some of my kids used to complain that I was more of Aurora than with them, what was true, I have to admit. So you get to know the animal pretty well, and it was really very, very interesting. That's the reason I like to pay homage to their contribution, because they were really almost like a colleague. They were there doing the experiments with us, and they were enjoying, and you could see that they were having fun, doing this thing.
At what point did you realize that you could harness the signals from their brain and transmit them over the internet?
Yeah, we have done several experiments before here at Duke with different preparations. But then we wanted to show that you could scale the effects of a brain-machine interface over 3 parameters: time, space, and force. So I always like to say, and in the book I say this several times, that this is a process. The brain-machine interface paradigm is creating conditions for the brain to be liberated from the constraints of the body, the physical constraints of the body, because now you can enact your voluntary will, in this case motor will, at a distance. So we wanted to prove that this could be done really very far from where the subject resides. That's the reason we had Idoia walking here in our lab in a treadmill, as you saw in the clip. Her brain signals were sent to a very sophisticated internet connection. This is not your typical internet connection. This was created by Gordon Cheng, a scientist, a roboticist that was in Japan at the time. Now he's a professor at the Technical University of Munich. He's also building our exoskeleton right now. But Gordon created a way that our signals, and these were brain signals, digitized of course, digital brain signals, could be sent to Japan very quickly and make the robot walk in Japan. And at the same time, the same channel could broadcast back to Idoia visual feedback, images from cameras that were tracking the legs of this robot walking in Japan, so that we could project in front of her, in this huge screen, the back of the legs of the robot. So she had a feeling walking the treadmill that she was looking at legs moving, and they were synchronized with her leg movements in the treadmill. And all of this operation was done, the round trip around the world was done in 220 milliseconds, what is about 25 milliseconds faster than it takes for an electrical signal to leave your head and get to your muscle in your leg. So we scale time. We reduce time for this operation to happen. We scale space because the legs that were moved were across the planet from the brain that generated the desire to move. And we scale force because that was an industrial humanoid robot that was much bigger than poor Idoia that was walking here. The interesting thing is that not only was Idoia able to keep these legs moving, but when we stopped the treadmill here at Duke and we continued to reward her every time the robot stepped on the ground, she got a treat, a food treat. She continued to control the robot without moving her own legs. So she was able to imagine what she needed to do for that robot to move without contracting any of the muscles that move her legs. And Aurora had shown that for upper limbs. But this demonstration with Idoia was even more dramatic because you now had a very complex behavior, locomotion, happening without any body involvement.
That seems kind of like how athletes do visual or mental preparation.
Yes.
So you're seeing this, you can, I guess, stimulate that in a monkey, but is that what athletes are doing when they do mental preparation?
Well, I don't know for sure, but yes, that's a very good hypothesis. Yes, very likely. That's what we call mental preparation, really, or mental rehearsal. I have read a lot about, very famous proficient athletes like Michael Jordan, Pelé, and others that claim that they, before a big game, they actually imagine some movements or some moves that they would make to fool the opposition, and they rehearse that in their minds actually before they actually did the true experiment of testing the moves. And yes, we could, and we know that what in our jargon we call motor imagery can be instructed in humans for sure. We knew in monkeys that could be done, but nobody had really recorded that activity and played it out for everybody to see like that. So we took advantage of this, and it seems that even primates can do that.
Speaking of elite athletes, you said in an earlier talk that for tennis players like Andre Agassi, they actually have an extension of their racket in their brain.
Yeah. Well, yeah, this is something that is becoming almost common sense in neuroscience, that every tool that we used and every tool that we become proficient in using. We are tool makers, right? That was one of the definitions of our species. In fact, some of our ancestors in Africa have been named by, famous paleontologist Louis Leakey as Homo habilis, right? The man that makes tools. But what I'm proposing is that we deserve a little more credit because not only we make tools, but our brain assimilates these tools as an extension of the model the brain carries of ourselves. So when you get, I like to say that the brain is a big simulator, a big modeler. So it creates a model of reality, and it creates a simulation that we call the sense of self. So this belief that we inhabit the body, right? That we know I can fool your brain in minutes for you to think that you're inhabiting a completely different body. And you will be fooled instantaneously. That has been shown several times now in the literature. In this case, what we propose with our experiments and other colleagues in other universities, that tools are assimilated. So if you ask a tennis player in a magnet, you're recording his brain, and you ask him after a game, a very intense game, to use the right index finger to point to where his hand ends, he's actually going to point where the racket was. Oh. He has the total sensation that his arm has extended to the end of the racket. Okay? So this is probably true for every tool that we use, cars, instruments that we play, when the surgeon operates, the scalpel, and every tool that we use, according to this theory, is part of us.
So we have a question here from Stuart in Durham, and it asks, as we move closer to human applications, how much of an obstacle to the good functioning of invasive brain-computer interfaces is scar tissue buildup in the brain? he says that he understands it can cause the signal to become weaker and even lost as the body reacts to a foreign object.
That's the same problem that cardiologists had when they start using pacemakers that you have to implant in the heart. So you have, every time you put an extraneous artificial material in living tissue, you will get an inflammatory reaction. And that inflammatory reaction produces a cascade of events that ends up with some scar tissue. So that is true for the brain too. Anything that you put in the brain will generate an inflammatory reaction. We actually take advantage of this inflammatory reaction to anchor our implants, because some of this scar tissue will actually make these fine microwires, because these are, as I said, like a hair, they're very flexible filaments, stainless steel or tungsten covered with Teflon. And as you leave this in the tissue for months, there will be scar tissue that anchors these filaments, and at the same time creates an interface that helps the recordings to become stable. In some of these filaments, you can have scar tissue that blocks the interface, so you lose the signal. But we learned that this is can be dealt with by several techniques. And even if you lose a few of these wires, since you have hundreds of them, you can overcome the inflammatory reaction. But that's a key issue as you move to human clinical applications, for sure.
And in terms of those clinical applications, one of our viewers, Rob, asks, will there be trials for Parkinson's patients at Duke? And if so, how does a person apply?
Yeah, we don't have the plans yet, because we have to finish the primate work. And there are many colleagues around the world doing the same thing. There are many laboratories in Europe, in Canada, here in the United States, in Brazil, testing. And that's very good, because you have independent groups testing the technique and seeing how far can we take it, what are the limits. I got already a few reports of neurosurgeons in different countries that try the technique in desperate cases. And in Canada, in Europe, I heard already. And these are anecdotal reports. They claim that they're going to publish these reports, and the results are very good. So I'm very enthusiastic, but we still don't have a plan defined for a clinical trial. Of course, as soon as we have the primate data and we have finished this, and we know that it's safe and it has the effects that we saw in the rodents, we will let people know, of course.
You mentioned Brazil, which is your home country, and you've been actually doing some work there in terms of science education, building an academy. Can you talk a little bit about that?
Oh yeah, that's my favorite hobby. Is this voluntary work that I do in Brazil that started about 8 years ago, creating a new concept of a new institute of neuroscience, but with a new concept. They use science as an agent of social and economic development in a very poor community. So we chose one of the poorest parts of the country in the northeast of Brazil and created what is today one of the largest scientific projects in the country, because not only has a state-of-the-art international neuroscience institute working with scientists and faculty and students, but it also is linked to a science education program that has already 1,000 students. Is going to be upgraded to 3,000 students next year. But this education starts, curiously, during the prenatal care of the mothers of our future students. So the mothers go to our clinic where we do prenatal care that didn't exist in the region, and we basically took a very high mortality rate for mothers to close to zero in the region just by creating a whole program that today oversees about 16,000 women a year. And as the mother goes through the prenatal care, she's learning about how to take care of the baby and how, what is going to be postnatal life. This kid is already being enrolled in our education program. So we are going to have a school that is about to be finished with the support of the federal government in Brazil that will take kids from birth all the way to high school, full-time schooling with half of the period, of course, after 4 years of age, of science education. So in labs, no talks, no classes. All the science education is going to be done in laboratories designed for children. So science education is achieving a complete different realm in Brazil. And what we are doing now with this pilot with 1,000 kids in Natal, that's the name of the city, is now being approved by the Brazilian government to be taken to other places. So we are looking at 1 million kids in the near future enrolled in this curriculum, which is phenomenal, I think.
And so you said that you had support from the Brazilian government.
Yes.
The president and everyone's been very supportive. Have you gotten any pushback from anybody, or is everyone very receptive to this idea?
Well, in fact, I should say we got support from all over the world. We got support from Duke when we started, and the provost of Duke, Dr. Lange, Peter Lange, helped us organize an international conference in Brazil where we brought 35 of the most distinguished neuroscientists in the world, a Nobel laureate, to talk about this project, to help. And then the president of Brazil, and then President Lula, called us to talk about this project and gave his full support. We had, it's a private-public project, so we got donations from all over the world. Brazilian expats living in Europe and in the United States made donations to this. So it's a very interesting mix of a private and a public collaboration. Yeah, we had some resistance, from people that didn't believe that high-quality science could be produced in such a poor neighborhood or pure community that is really poor in the Northeast, in the outskirts of a city that is very nice, very good, but has very serious social issues. And we proved all them wrong, because not only we got scientists, high-quality scientists, to come from all over the world to work there, but we also got our kids that live today in the worst school district of Brazil, or one of the worst school districts in the country, to, after just 3 years in this science education program, to reach a level of performance that competes with the best private schools in Brazil. So it can be done, and it was an experiment, it was a social experiment that proved the critics who said that you could not take high-level science to that part of the country wrong, actually.
So how did you go from your neuroscience work to this educational outreach work?
Oh, I think it's all connected, because I truly believe that everything that we do, everything that humans do, have done, do, and will do, is somewhat related to how our brains operate. Our political systems, our economic systems, our education system, it all comes as a projection of the neurocircuits that operate in our heads. So, believe it or not, we grew up thinking that physics is at the head of everything in life, right? Scientists love to put physicists on top of the pyramid, and we come way down there, poor biologists looking at this thing called the brain. After all, it's just a mass of tissue. I inverted the pyramid. I truly believe that to understand anything or to do anything meaningfully, you need to understand the master who created everything. And the master who created everything around us, this illusion that we call reality, is called the brain.
And so let's close with a couple more questions regarding your book. We've got one from our viewer, and he says, okay, brain to robot, I get that. What's this brain-to-brain thing that you've mentioned in your Scientific American article, the BrainNet?
Well, this is, of course, a futuristic view, is a speculation that you cannot do in scientific journals. So when you write a book, you have freedom, because you have an editor and yourself, and you take chocolate to the editor and you convince the editor that you can get away with some of these things. Well, I'm thinking about way ahead in the future, and when we will be able to communicate with our computers, with our appliances, and eventually with ourselves, just by thinking. When we are going to have non-invasive techniques that read these magnetic, very tiny magnetic fields that come off here in the scalp, that carry all our intentions, emotions, and will to communicate to someone else. And someone else will be able to understand that, and will be able to communicate in a much more truthful, in my opinion, way, because there'll be no barriers. Language is a barrier. Language is like a filter. Writing and speaking introduces filters to the thoughts that we generate, and they are not completely precise in terms of explaining what we mean. Just look at emails, right? How many confusions you got or I got just by writing a sentence that people interpret in a completely different way than you meant. What I'm foreseeing is that in the future, this technology that started, with these simple motor tasks, one day will evolve to a new channel communication. So imagine being an internet or in a network in which you don't need to type, or you just think of what you want to post, and you receive this information directly in your brain as signals that your brain can decode. So that will multiply several orders of magnitude the way we exchange information, and the way I think we will understand people. And that's what I call the BrainNet.
Okay. So you mentioned this idea of language being a boundary or a barrier.
Yes.
When you're communicating brain to brain, will the language be, I guess, some kind of computer or digital code?
Yeah, that's a good question. First of all, it will come from the innate mechanisms that generate our intentions, right? It will come directly from these brainstorms. And that will be transmitted. First will be recorded by some technique that we don't have today that will allow us to do what we do today with the motor signals, right? Transform them in digital commands that can be broadcasted very quickly, light speed, and then it can be delivered. And we don't have a technique to deliver that. We have some attempts that are just starting, but in a few hundred years they will be here. So they will be delivered in a way that we today deliver signals from robots back to the brain of our monkeys in electrical messages that your brain is going to decode very easily because that's the language that the brain utilizes. So, of course, all of this is way ahead in the future, but I can envision the possibility as a complete new form of communication.
Way ahead in the future. How far ahead? Hundreds of years?
Well, it's difficult to say because we have these exponential jumps, right, in technology development. When I sent my first proposal to NIH 12 years ago saying that I would make robot arms move with just by thinking, people send me a psychiatric recommendation, find the next best hospital to do. And in 3 years we did it. And I met the reviewer afterwards and he was pretty, shocked. That we could do that. So it's difficult to say, but I need to tell you that all the major computer companies, internet companies in the US and Europe, Google, Microsoft, Intel, all the big companies have now divisions or groups of brain-machine interfaces. They're already thinking of ways, non-invasive ways, for us to interact with our operating systems in our desktops or laptops that do not involve the usual interface. So when you put all these bright people working together and you have a huge network of neuroscientists, investigating the brain, the impossible may become possible in a shorter period of time.
We wouldn't need Facebook or Twitter or
Flickr. We may need, but the speed on which this will be transmitted beats all the social networks that we have today by a long shot. So you transmit images that come from your retina directly to the ones that you allow to see what you're seeing. So there are many beautiful applications of this. You will donate your vision to people that cannot see, for instance. I can see a mother donating vision to a son that cannot see. But these are in the future. I mean, I think the applications of brain-machine interface for medicine, the motor rehabilitation, or even sensory rehabilitation, vision, audition, prosthetic devices that will restore vision and other sensory modalities are pretty much coming up in the next decade. And eventually, interfaces with our computers, I think also are in the middle term of the future.
Well, thank you. I think we'll close with that vision of the future. It was a pleasure to have you on the show. Office Hours is back next Friday at noon. We hope to hear from you during our conversation of education reform. Send us your questions via Twitter and Facebook.
Produced by Duke University.
Great.
Online at duke.edu.